Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and this is another lecture in the course Analytic Methods for Lawyers. It's about causation, which is one of the most important issues in the law. And what we're going to do is to try to explore statistical approaches to causation. I'm going to do it by starting out in this first of 4 parts by telling a kind of artificial story involving a hospital that has 2 potential treatments for kidney disease. And we're going to see that uncertainty as to the causal relations between various factors that might affect kidney disease leads to different estimates of the efficacy of the 2 treatments. Now, I'm not going to use a lot of terminology here, but we are going to see what we're later going to understand are confounders and colliders. We're also going to actually see something called Simpson's paradox and Bergson's paradox. I'm not going to show you in this video how to solve the problem of causation. Well, that'll wait for later videos. But we are going to see how the failure to take causation into account can cause a lot of problems. The good news is that unlike 20, 30 years ago, when you might have just thrown up your hands about causation, today it turns out there are a lot of things you can do to improve your understanding of it. Okay, so let's get going. We've got this hospital and it has 2 treatments for kidney stones. Treatment A is the new treatment and treatment B is the old treatment. And they've been keeping some data on how patients have reacted to the 2 different treatments. I'm about to retrieve that data. You should know that the data actually is the same data that's used in many pedagogic expositions of causal inference. If you look at the Wikipedia entry, for example, on Simpson's paradox, which requires a little bit of an understanding of causation, you'll see that it uses the same data that I'm using here. All right, let's go get it. Let's bring in this data. It's importing it. You can see we've got data on the size of the kidney stone, the treatment used, and the outcome for each patient. Now, it's a little perhaps challenging to remember whether one is good or one is bad, and so someone suggests that it might be easier if we just adjust the data set to show a written description of the outcome. So let's do that, and we now see what the outcome is. Okay. So let's do something naive, which is just to group the data by treatment, show the outcome, and then see whether the outcome is good or bad. All right, we do that, and we can see that for treatment A, there's something like a 3-point-something to 1 ratio of good outcomes to bad, whereas for old treatment B, it looks like the ratio is higher. And so, if you just look at this naively, you might think, you know, those old treatments, those time-tested treatments might be better. And in fact, rather than guessing at the ratio, we can actually compute the ratio, and you can see that treatment B has a good outcome a little more frequently. And if anyone here knows someone who's got kidney stones, you know that that little 4.5% difference is actually a big deal. Kidney stones, I don't have any, but they're reported to be extremely painful. All right, so one of the things that we can do is we can see if the difference is statistically significant, and what we're going to find is no, but it's not too far off. The other thing we could do is do a logistic regression of outcome on treatment. Here's the form that we need. We need our 2 variables, treatment and outcome, and we're going to do a logistic regression here. Yes, you could do machine learning, all sorts of things that you now know how to do. And what you see is that the p-value using logistic regression is very similar. The other thing is that we're not really explaining too much of the variation in outcomes. So, Jane, one of our researchers, is suggesting that perhaps the size of the stone might be important to the outcome of treatment. And so we're going to do a little bit of programming here. We're going to group the data by the size, we're going to group it by the treatment, and we're going to look at the outcome. All right, so we've got our data here for the small stones and the large stones. I will say, staring at this, it's a little bit hard to figure out whether A or B is better. And so what we're going to do is to compute some percentages. All right, and it turns out that for small stones, A has a higher fraction of good outcomes than B, and for large stones, A has a higher fraction of good outcomes than for B. And if you're paying attention, you should be very, very troubled by what I just found. Because, let's go back. B has a higher percentage of good outcomes than A. And yet, for people with small stones, A does better than B. And for people with large stones, A does better than B. Surely I made a programming error. But in fact, I didn't. Jane didn't. What you just saw is something called Simpson's paradox, in which overall you have B is better than A, and yet for each group, A is better than B. Good thing Jane paid attention in her biostatistics class. She remembers how you escape Simpson's paradox. What she's going to do is to make a plot in which, let's actually make the plot and then I can explain it. Okay, so on the x-axis here we have the fraction of the group that in fact has small kidney stones. The brick color here is the fraction of people that would have a good outcome. And you'll notice it runs from 68% up to about 84%, which is going from here to here. As the fraction with small stones increases, the fraction of good outcomes increases. The aqua line here represents again, we're going to take the fraction of the group with small stones and vary it, and we're going to see how the good outcome goes. It looks like it goes from about 73% up to like 92%, which is exactly what we see in this chart. And so let's actually now annotate Jane's graph, and you can see how Simpson's paradox is emerging. For the group that got treatment A, there's a much smaller fraction that actually has small stones. A tends to be used on people with big kidney stones, whereas for the people who got treatment B, they have a much higher fraction of the easier to fix small kidney stones. And so this difference here between this number of like 83% and this number of like 78% is reflecting the fact that the two groups, the group receiving treatment A and the group receiving treatment B, are not the same. And so this is an explanation of why Simpson's paradox is appearing. You could think of it as the following. Supposing you got instruction from either Professor A, who was a fantastic constitutional law professor, or Professor B, who was only a mediocre constitutional law professor. Now, if Professor A got the students with lower aptitudes, precisely the ones who needed his brilliance, and left the better ones for Professor B, if you did a study of how the students performed, it might end up that it looked as if Professor B was a better teacher than Professor A. In order to really compare Professors A and B, or treatment A and B, you would benefit from a randomized controlled experiment in which you decoupled the aptitude of the student, read size of kidney stone from professor selection, read treatment received. What we're about to see, though, is you actually don't need, if you understand causal inference, to do the randomized controlled experiment. You can actually deduce a fair amount from the data itself. Okay, here's what Jane's going to do next. She's going to group the people by treatment, and then she's going to group the people by the size of their kidney stones. And now let's take a look at this. Okay, and what you see is that group B, in fact, has a lot of people with small kidney stones, whereas the people receiving treatment A doesn't have that many people with small kidney stones. So we've basically figured out why Simpson's paradox is happening. Another way to go about it is to do a logistic regression in which the features, the independent variables, we'll sometimes call them covariates, are not just the treatment received, but also the size of the kidney stone. Those are nominal variables, so I've told it that there. And let's get a parameter table and one of those pseudo R-squareds. And when we do that, we find that treatment A actually has a positive effect on the log odds, which is, roughly, well, we've discussed what log odds are, kind of like probability, but not, on having a good outcome. So we're still not explaining a lot of what's going on with kidney treatment in this hospital, but still, once we simultaneously control for the size of the kidney stone, which is itself a negative factor, it turns out that now it looks as if treatment A has a positive effect. Notice we want to contrast that with what we saw when we did that initial logistic regression, which is that when we didn't take size of the kidney stone into account, it looked as if treatment A had a negative effect on the outcome of the patient. All right, so to summarize, it's looking now as if actually treatment A is causing a better outcome. Among people with small stones shifting from B to A, looks like it increases the probability of a good outcome by about 6%. And among people with large stones, it looks as if it improves the outcome by, I don't know, 4-point-something%. So, and we can actually do a little bit of coding here and take a look at that more precisely. And yeah, you get 6.4% for small stones and 4.2% for large stones. So what have we learned? We've learned that a variable that we've got in our data, stone size, provides information both about the treatment one receives and provides information about the outcome. And so if you ignore stone size, the associational thing you might get from doing a somewhat naive logistic regression, the kind of thing I showed you here, might give you a misleading outcome, and actually that could have a serious effect in the real world. Basically, size is acting as a confounder. It's making it appear that treatment B is better, whereas in fact, it might well be the case that treatment A is better, regardless of whether you've got small or big stones. But before we make a final conclusion about that, we need to do a little more work. Now enter Dr. Eager. Dr. Eager sees how successful Jane has been in untangling causation and thinking about confounders, and he thinks, you know what? Maybe the ward the person is assigned to makes a difference. He should search for other factors that might matter. And so Dr. Eager asks some unlucky intern to get the data on which ward each of those patients was assigned to and add it to the data set. So let's see what that intern found here. And just a moment, we should have it. All right, there we go. And you can see we've now added a data on whether the patient was sent to the Lecter ward or the Watson ward. So now what Dr. Eager is going to do is he's going to group the patients by the ward and then look at the outcome. And yeah, it does seem to make a difference. Among patients who got sent to the Lecter ward, there's only about a 1.5 ratio between good and bad outcomes, whereas patients who got sent to the Watson ward, that looks like, almost 7-to-1 in terms of a good outcome. And so Dr. Eager wants to do another regression. Maybe the nurses in the Watson ward are much better. So he's going to regress outcome on size, treatment, and ward. By the way, to do this, he's going to need a function called bool. Here's what bool does. Bool of 7. Actually, that's not a very good thing. What we want is bool of true. That yields a 1. And bool of false yields a 0. So it just turns a true or false into a 0 or 1 because you need to remember that logistic regression kind of wants the outcome variable, the target, to be a 0 or 1. So we'll run another logistic regression here. And now what do we see? Now we see, first of all, that being sent to the Lecter ward has a very significant negative effect, or I should say, is associated very strongly with a bad outcome. And we see that we actually perhaps underestimated how important treatment A was. Before, when Jane just looked at size and treatment, we got a coefficient of 0.357, but Dr. Eager seems to be showing that no, actually treatment A has a coefficient of 0.777. We really need to get people on treatment A. Dr. Eager is very proud of himself because the ward's incredibly important. We can now predict much more. And Jane, sure, she had some insight, but she'd actually underestimated how much better A is. All right, and now someone else speaks up at this meeting of hospital researchers. It's Dr. Pearl. He's considered a curmudgeonly genius, and he says, no, 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 you've got the causation backwards, and as a result, Dr. Eager, you've overestimated the effects of treatment A. Jane did it the right way. Here's what Dr. Pearl explains. First of all, regression can't determine causation. If you did a regression of hours of sleep per night on car accident frequency, you'd likely find a negative and statistically significant coefficient. But car accidents don't cause sleep deprivation. Sleep deprivation might cause car accidents, or maybe there's a common factor, poverty, that causes both sleep deprivation and car accidents. But the problem that we have here, Dr. Pearl says, is something known as collider bias. And he says, look, supposing variables x and y are completely independent of each other, x doesn't cause y, and y doesn't cause x, but x and y both cause a third thing, z. Now, Dr. Pearl loves Wolfram language, and so he asks you to gather around his laptop and watch the following, because he likes to do things instead of just say them. So here's what we're going to do. We're going to say, we're going to create some x values. There we are. We're going to create some y values, and you'll notice y doesn't know anything about x, and x doesn't know anything about y. But we are going to have a third thing where both x and y contribute to this z value. So Dr. Pearl, who's very good at Wolfram language, puts it all together and he makes a little data set. Here it is. We've got 1,000 pieces of data which have an x value, a y value, and a z value. Now, says Dr. Pearl, let's do a regression of x and z on y. We're going to try and predict y using x and z. And what do we find? We find that x is associated with y, and the p-value is tiny. But wait a second, how can that be? How can x and y be negatively correlated when by construction y didn't know anything about x and x didn't know anything about y? That's what Dr. Pearl is concerned about. And Dr. Pearl says he has an explanation. Let's look at it. What we're going to do is we're going to make a little causal graph where x is determining z and y is determining z. All right, there's our picture. Here's what Dr. Pearl says. If you look at z, you've got two arrows coming into it. It's colliding. And, says Dr. Pearl, it is very, very bad in statistical analysis to control for colliders in a regression. Z is a collider. And by controlling for it, which we did when we included it as an independent variable in our regression, we mucked everything up. Not only is it bad to include z, says Dr. Pearl, what if z in turn caused alpha? Let's look at a graph. For example, alpha might be the cafeteria from which the patients were served, and the particular cafeteria used might depend on whether you were assigned to the Lecter ward or the Watson ward. Could you add cafeteria to your regression? See, here it is. Z is causing alpha. Is that such a bad thing? And maybe it's just Dr. Pearl is jealous of Dr. Eager's insight. But in fact, Dr. Pearl is quite right, and he thinks he can come up with an intuitive explanation for this phenomenon of collider bias. Here's what he's going to do. He's going to plot x and y together. All right, let's do it. There it is. There's our x and y values in the data. There's the best fit, and that looks pretty darn flat. Yeah, there's a tiny downward slope, but it's really pretty darn flat. But now, let's color the points according to the z value. So that's what I'm doing here. We're going to only select when z is equal to 0. There are the points, the x and y values for when z is 0. And we'll also now do the same thing for when z is 1. And what you can see, and I fit the best line, what you can see is that by controlling for the z value, you induce a correlation that formerly didn't exist between z and y, and that's true whether you pick z equals 0 or z equals 1. And so, says Dr. Pearl, if ward is a collider, if ward is determined by treatment and outcome but doesn't cause outcome, it's really bad to include it. It biases the estimate of the effect of treatment A versus treatment B. The point Dr. Pearl makes is including ever more variables in a regression is not the right answer if you're concerned about causality in statistics. The people in the room shake their head, they don't get it, and Dr. Pearl says, look, people never understand him at first, and he says something, this Bergson's paradox, but he doesn't want to explain. We got one more researcher in the room. It's Dr. Liberal. Dr. Liberal says maybe we've got it all wrong. Maybe the main factor in outcomes isn't the treatment you get or the ward you're stuck in. Maybe it's how much support you have at home. Dr. Liberal's a big believer in the social determinants of health. So Dr. Liberal's very frustrated that the data didn't include anything on social support. So he persuades the National Science Foundation to get $1 million grant to go back and try to determine the level of support that each of the persons who got kidney treatment at this hospital, what their social support level is. And so let's take a look at it now. There it is, and you can see we now have the data obtained at great expense on the social determinants of health. And so Dr. Liberal says, I'm going to do a regression also. And I heard Dr. Pearl, so I won't stick ward in, but I am going to do size, support, and treatment. So let's see how that works. And now it turns out that support is a positive factor. Yeah, the p-value isn't quite there, but it's not too far off. And the treatment value of 0.35 starts to look very similar to what it did when we didn't include ward. Let's go all the way back here. See how it's like 0.3572? And now after we've added in social support, although support is, got to keep moving down here, it is a factor. It doesn't affect the estimate of the effect of treatment A. Treatment A is still better, and it increases log odds by 0.35. And Dr. Ward decides, you know what, maybe I should include ward. I don't know what Dr. Pearl was saying. He never understood stuff. Never understood Dr. Pearl. So we'll add it back in, and what we see is sort of the same picture. The effect of ward isn't much changed. The effect of treatment A goes back to being 0.77, much greater than it was before, and we have a higher R squared than we did before. So we've still got a little bit of a puzzle as to whether Dr. Pearl was correct that we shouldn't include ward, but what we're seeing is that the effect of treatment A seems to depend on what features, what independent variables we include in our regression. So we've got an intellectual cliffhanger before us. We've got different voices, and we're not really sure whether to use treatment A or treatment B at this hospital, and lives actually rest in the balance on this. So my point here is simply that different models of causation, different features to include in the regression can affect the results greatly. The next videos are going to be more technical, and they are going to provide suggestions on how to resolve the problem. You're going to learn, by the way, if you haven't guessed already, that Dr. Pearl is correct. There's a reason that people regard him as a genius, and you will be able to understand his point better at the end of some of the later videos. That's the end of our introduction to causal inference. We'll see how to resolve it, as well as other methods in causal inference in later videos. Thanks very much.